we present a novel method for generating animated painterly renderings of participating media, such as smoke, fire, and fog. Given a dynamic 3D scene, our objective is to compose a single layer of opaque or semi-transparent strokes in screen space to represent both volumes and surfaces in a unified manner. By animating these strokes, we produce expressive, stylized depictions of the underlying scene. Participating media introduce unique challenges distinct from those of surface geometry. Due to volumetric occlusion, multiple 3D points may project to the same pixel, complicating the design of spatial features necessary for stylization. To address this, we leverage a fundamental connection between surface and volumetric visibility. Surface visibility corresponds to a delta function along a ray, while participating media are characterized by the free path distribution, a smooth probability density derived from the extinction coefficient. As the extinction coefficient increases, this distribution converges toward a delta function, allowing volumetric media to behave increasingly like surfaces. This observation enables us to define features and basis fields that generalize smoothly from surfaces to volumes. For instance, intensity values are computed directly from the rendering equation, while apparent curvature, which is typically ill-defined for volumes, is estimated by weighting isosurface curvature with the free path distribution. By using transmittance to define the isosurface, we achieve stability under moderate density variations. The resulting curvature converges to surface curvature in dense regions and approaches zero in transparent areas, aligning with perceptual expectations. Additional features, such as apparent relative velocity and mean free path, further enhance the expressiveness of the stroke representation. To reduce manual effort, we introduce an automated exemplar selection algorithm. Based on the distribution of features across all animation frames, the algorithm selects a compact set of representative frames. The user provides exemplars for these frames either by directly painting them or by stylizing rendered images. Stroke attributes such as length, width, and orientation can be specified through simple annotations, enabling fine-grained artistic control with minimal user intervention. Next, we present a series of results created using our method. We begin with the rising smoke example. A single column of smoke rises under animated lighting and camera motion. The generated strokes follow the swirling flow and smoothly transition across dense and sparse regions, maintaining stylistic consistency throughout the sequence. In the clouds example, a swarm of clouds moves toward the viewer. Dense clusters rise and gradually thin out as they dissipate. The use of opaque strokes vividly captures these transitions, conveying the evolving structure of the clouds. The colliding smokes example shows multiple colored smokes interacting and merging. By incorporating additional features from the A-star and B-star channels, our method accurately distinguishes between different materials and captures their natural blending after the collision. Next, we present the laminar to turbulent flow example. As the flow transitions from smooth laminar motion at the top to turbulent motion below, our method adapts seamlessly, preserving coherence while faithfully expressing the shift in dynamics. The ring fire scenes illustrate fire and smoke emitted from a ring-shaped source. In the first setting, with a higher extinction value, black body radiation diminishes as the fire cools outward, giving rise to dark smoke. Our method effectively captures this transition. We also show a variant with lower extinction, highlighting how extinction influences appearance and stylization. In the dense static medium example, a homogeneous static volumetric medium produces solid-like subsurface scattering. Our method consistently transfers the intended style from the exemplar to each frame. In the surface-only example, we demonstrate a scene composed solely of surface geometry. Although minor temporal artifacts may appear near occlusion boundaries due to screen space stroke placement, our method successfully stylizes most regions with high fidelity. The wood and fire example showcases a hybrid scene featuring flames, smoke, and wooden objects. Our method accurately distinguishes between these materials, producing smooth and coherent transitions across different regions. In the foggy forest scene, volumetric fog flows through a forest of trees and grass. Here, in addition to the four core stroke attributes, we utilize region labels transferred in a manner similar to color. These labels guide stroke termination, helping to distinguish between different materials and improve visual clarity. The fire example presents an alternative setup where strong upward flow stretches flames and smoke vertically. We also show a variation rendered using a stroke shader that mimics a plausible pencil drawing style, and another variation using a shader inspired by charcoal drawings. We also demonstrate cross-scene style transfer, where learned stroke behaviors from one scene are applied to another. For example, transferring the style from the fire example to the ring fire scene, or from rising smoke to laminar to turbulent, yields coherent and visually consistent results. For transparent styles with Kubelka-Monk-based color blending, we apply a post-processing step that adjusts stroke colors to better align with the intended color attributes. Lastly, we briefly highlight some of our additional studies. For comprehensive results across all scenes, including ablation studies and validation of attribute transfer accuracy, please refer to our additional video and supplementary document. First, we demonstrate temporal continuity across frames for our transferred stroke attributes: color, length, width, and orientation. This illustrates our method's ability to maintain consistent and coherent stylization over time. Next, we show how the system responds to different user annotations. When lengths and widths are uniformly fixed across space, the resulting strokes show reduced variation. In contrast, reversing the original annotations, for example, assigning longer lengths where short ones were intended, produces long strokes in complementary regions. We also compare our method with prior approaches, including patch-based synthesis, neural style transfer, and diffusion-based text-to-video generation. These methods often suffer from stitching artifacts, poor stroke structure, or limited artistic control. In contrast, our technique produces more expressive, stable, and coherent animations. In addition, we compare against alternative feature representations, specifically image-based and isosurface-based features. Image-based approaches are prone to noise due to motion estimation errors, while in the clouds example, the isosurface-based method failed to compute geometric features due to degenerate geometry. Our volumetric features, by contrast, preserve structural fidelity and stylistic stability throughout the animation. Finally, we present an ablation study evaluating the contribution of different feature and basis field groups. Removing illumination-related components introduces noisy color variation. Omitting normals, curvature, or additional volumetric cues leads to flatter, less expressive outputs. Excluding silhouette-related components can reduce the stability of the transferred attributes. Without velocity features and their associated basis fields, strokes fail to align with the underlying motion. These results underscore the importance of adaptive feature selection in achieving high-quality, coherent stylization. Thank you.